Hi Prof, welcome to our video. Hope you had a great day. Today, we are going to explore both relational and non-relational database, compare them with each other, and finally recommend the Ministry of Healthy Lifestyle on which is the suitable database model they should adopt for their Fitness 365 application. We redesigned the initial database such that we reduce data redundancy and improve data integrity via normalization. Firstly, we included the first name and last name attributes in the user table such that the identity of user can be queried rather than just their username. Secondly, we decomposed the unary relationship of user table, forming a weak entity called following. We then take the primary key from the user table as the foreign key of the following table, forming a composite primary key. Thirdly, for activity table, activity spot, activity name, and description were removed. After removing activity name, we created an activity type table to categorize and label activities names with activity type ID. Next, the participants table was formed from the decomposition of the binary many-to-many relationship between user and challenge. Both the primary keys of user table and challenge table were used as the foreign keys in participants table, forming a composite primary key. Similarly, the membership table is formed from the decomposition of the many-to-many relationship between user and club. Both the primary keys of user table and club table were used as the foreign keys of membership table, forming a composite primary key. Lastly, we added a privacy control table where users are allowed to decide their privacy control for their accounts. Users can choose between followers only, where they only allow the followers to view their posts, comment, and give kudos to their activities, or private only, so that no other users will be able to see their posts other than themselves. After all the changes made to the initial database, this is our final entity relational diagram. The assumptions we made include one activity can only be completed by one user, which means activity cannot be shared between a group of users. Next, users can only create their own activity where there is no tagging of activities allowed. Next, every club can only have one activity type. For example, if the main activity of the club is running, users cannot add their swimming activities to the club. Also, challenges must have minimally one user. Then, challenges can only be started by clubs, where individual users cannot start their own challenge and clubs can start more than one challenge. Lastly, challenges started by club must be of the same activity type as the club's main activity. Now, I'll pass my time to Jalvin, who will bring you through the SQL queries.
Thanks, Pezza. So the first requirement requires us to generate a list of male users who are more or equal to 20 years old. So here we just need to select their usernames from the user table where the gender is male and the age is more than or equal to 21. For this query, we derive age by using the current year less the year from the user's date of birth. Next, we look into question 2. In the first nested selection, it generates a temporary table that counts how many males a male user are following. Similarly, in the second nested selection, it generates a temporary table that counts how many females a male user is following. Lastly, the two tables join based on their user IDs, and the result is filtered by the condition that the number of females is more than the number of males. Next, requirement 3 is to generate a list of female users who are only followed by male users. First, we created a temporary table of female users that are followed by female users using the following table. We then selected the user IDs of the female users who are not in the temporary table as mentioned earlier. We then obtain the usernames of these user IDs from the user table. Next, requirement 4 is a list of users who are mutually following one another. So here, we first did a left join of user and following tables on user ID equals to follower ID. And this will be a temporary table. The next temporary table is another left join of user and following tables, but now it's on user ID equals to followee ID. We then did an inner join of these two temporary tables. What this does is to get a list of users who are mutually following each other. So from this table, we simply query the usernames to obtain a list of the pairs. Next, requirement 5 is an activeness insight which shows the duration of activities done. Firstly, we natural join the activity and users tables. Then we selected the user's information, the sum of the activity duration as the total time, and the sum of the activity duration divided by the number of weeks as the average, where we will then specify the weeks that we are interested in getting the insight from, and what category that we want. Here, category is created by the case function, where we classify the activity durations accordingly to the requirement and give it a temporary name, which we then use as a condition to explain, to query the above explained for the user's information. Next, requirement 6 is merely an extension of requirement 5 with the addition of a classification of age. So the same logic applies. We first do a natural join of the tables, select the relevant information just like above from the join table, specify the conditions which we are interested in finding an insight from. In this requirement, it requires an additional case function where age is classified and then named accordingly to the requirement. This would then be a condition which we specify in the query to get the results. So basically, we are adding the classification of age to the previous query and adding it as a condition as well. Next, requirement 7 is another extension of requirements 5 and 6, this time with a classification of gender. Since there is no need to use the case function to classify the two genders, we just have to add gender as a condition to be specified while querying from the natural join tables as mentioned above. Requirement 8 is a list of users who received more than 5 kudos on average for each activity. Here, we first do a right join of the users table and kudos table on both activity ID. Then we are required to get the average kudos per activity by using the count function divided by the count of distinct activity ID in the activity table. Then we created two temporary tables to query from, the user and the join table. Lastly, we query the username from the join tables, specifying the average kudos as more than 5 as a condition using the where function. Next, requirement 9 is a computation of monthly active social networks, for where each user we have to list their followers who gave more than 5 kudos for each month's activities. We first did a join of the activity and the kudos table on activity ID. Then we join again with the user table on user ID this time. We then queried from the join table the username, the count of activity IDs as the number of kudos, having the count of activity ID more than 1 and the count of number of kudos more than 5. Next, requirement 10 is a social comparison analysis for where for each user the weekly average distance and the weekly average activity duration will be obtained. We first use a temporary table K to obtain the averages of the specific user and the range of weeks that we are interested in. The bottom part of the query gets us the specific user which we are interested to get, and so this will find us who the specific user is following. We then query the necessary information from 3 tables, K, activity, and user on the conditions that specify that one individual user and his or her followers and the averages using the sum functions divided by the number of weeks. So this is all for the SQL queries. I'll be now passing on my time to Melvin, who will elaborate more on the NoSQL part of the project.
Thanks, Jelvin. Now we'll be moving on to talk about our non-relational database model. One key feature of the database is that it has a flexible schema design. This means that it's easier to update the database to handle the ever-changing application requirements. Next is designed to handle unstructured data, which can be useful in applications that doesn't require data integrity. As such, we model our data from the relational database into the following 3 NoSQL collections, namely the user following, user activity kudos, and mutual following. In user following, it includes the user's personal details and the names of the follower and followee of the user. For the user activity kudos collection, we merge the activity, user, and kudos table from the relational database. This includes the names of the kudos giver of each activity. For the mutual following collection, it is a list that contains information regarding follower and followee relationship between 2 users. Now we will move on to the NoSQL booster to visualize the query. For question 1, we use the find function and filter the database by the male gender as well as the age more than 21. For question 2, we use the project function to generate a temporary document of users together with their gender information and the number of female and male followees they have. Afterwards, we use a match function to filter out the male user that follows more female users than the male users. For question 3, it is similar to question 2, however, we count the number of followers instead of followees. Lastly, we use the match function to filter out the female users that only has male followers. Now I'll pass on my time to Noah to continue the queries.
Okay, thank you, Melvin. So now I'm moving on to requirement 4. We are using the attributes called does username 1 follow username 2 and vice versa in our mutual following collection. You can easily find a list of mutual followers where the condition for both attributes are yes. And this is the output we obtain. So for requirement 5, for this, we use the aggregate function as well as the user activity kudos collection. Firstly, we use the match function to limit the range of weeks we wanted to query, which are from week 1 to 5 in this example. Next, we group the activities based on the usernames and added a new field that calculates their average activity duration by dividing the sum activity duration by the number of weeks specified, which is 5 in this case. Finally, we use the match function one last time to query for the range of average activity durations that was specified in the requirements. And this is the output that we will obtain. So for requirement 6, the only changes we made from the previous query was to add an additional condition in the first match function to include the age ranges as specified in the requirements. For question 7, the only changes we made from question 6 was to further add an additional condition in the first match function to include the genders that we wanted, which were either male or female. For this, for requirement 8, we used the same function and collections as question 7. Firstly, we grouped the activities by their usernames and calculated the mean number of kudos received to the length of the kudos giver array. We then used the match function to find those with a mean amount of kudos received of more than 5. For requirement 9, we also used the same function and collection as before. Firstly, we unwinded the kudos giver attribute for all activities, giving us a separate document for each kudos giver. Next, we used that match function to specify which user we wanted to query. After that, we grouped all of the documents by username, kudos giver, and month in order to obtain individual documents that summed up the number of kudos given from one user to another. Finally, we used the match function to obtain documents with a sum of 5 or more kudos given, and this is the output we obtained. So for our last query, we made use of both the user activity kudos and the user following collections. First, we used the lookup function to insert the appropriate user following document into each document in user activity kudos, using the attribute username as the connecting fields, and we name this inserted attribute following. We then use the match function to obtain the activities that fit the range of weeks desired, as well as either those that match the desired user's username or the users that they followed through the use of the female followers attribute within that following document. Next, we group them by their usernames and sum the total activity durations and distances. Finally, we added a field that calculated their activity average durations and distances based on the number of weeks as determined earlier. Now I'll pass my time on to Xiaoping.
Thanks, Noah. So, after viewing the querying process for both relational and non-relational database, you might already have an opinion on which database might be better for MHL's fitness app. However, let's have an overview on each database model objectively before deciding on which model to recommend. For relational SQL database, the enforcement of atomicity, consistency, isolation, and durability is required. These features help guarantee validity of database even in the event of system crashes, power failures, and other errors. Other benefits of having ACID transactions include absolute data integrity and safety. It also has a simplified concurrency control method, allowing transactions to be executed sequentially. SQL database helps reduce insertion, deletion, and updates anomalies through enforcement of referential integrity. Hence, it is commonly preferred for commerce and financial applications. The data structure for it is also fixed and not expected to change in the future. Hence, integrity of the data is required. For non-SQL, it is commonly implemented when there is a need for rapid application development, since non-relational database can support rapidly changing designs and coding sprints, which are more suited for agile applications which requires often data changes. Large amount of data can also be stored with little to no structure. With a flexible schema, it allows for more versatility integration of additional systems in the future, increasing its scalability. Here is a table for the other differences not touched on previously between a relational and a non-relational database. To summarize, a non-relational database is generally more flexible than a relational database, while a relational database proves to be more structured and organized than a non-relational database. I'll now pass on my time to Siwei to identify which model is the most optimal for MHL to implement.
Thank you, Xiaoping. So based on the comparisons done, our team recommends MHL to implement a non-relational database for their Fitness 365 application. So firstly, as the technology for wearable devices become more advanced, more users will start to use such devices that act as sensors to record new types of information like heart rate, blood pressure, and altitude. These new inputs can be easily added on the fly as new properties to non-relational database. We also expect that not all users will wear such devices and generate these types of info. Thus, inputting such new columns into a relational database will violate the normal forms with the presence of multiple null values. This is unlike non-relational database, which contains documents that can have different number of attributes present. Secondly, MHL is hoping to reach out to over 5 million citizens, so the dataset generated is expected to be immense. Non-relational database is preferred for this reason as they are horizontally scalable. MHL can easily add more servers to their database system to handle the large flow of activity information. It will also be more cost efficient for MHL to scale horizontally as compared to the vertical scaling of relational database, which is limited to the capacity of a single machine, and scaling beyond that involves much higher costs. And lastly, the data to be stored is exercise activity related info of non-critical nature, unlike critical info such as financial transactions maintained by banks. Thus, it does not matter whether the database possesses the ACID properties of relational database, such as consistency. And so it will be more beneficial for MHL to adopt a non-relational database to improve performance. So this allows the database to be flexible enough to meet performance requirements in order to accommodate the rising traffic of data generated during the app peak usage periods. So this marks the end of our presentation. Thank you.